What if the edge of the universe is not a place, but a question? There is a place in the sky where sight itself ends. We build bigger telescopes. We measure faint glimmers across billions of light years. We calculate the curvature of space, the velocity of galaxies, the residual glow of the Big Bang, and still we hit a boundary. Not a wall, not a cliff, not some cosmic brickwork hemming us in, but a silence, a dark, aching silence beyond which no light has ever reached us. We call it the cosmic horizon, the farthest edge of our visible universe. Not because that's where the universe ends, but because that's where the story, as we can read it, fades to black. Please like and subscribe, because this journey will change how you see our place in the universe. Prepare yourselves. We begin. This edge isn't physical. There is no dome, no final galaxy swirling like a celestial full stop. What we call the edge is really a limit in time, a prison made not of walls, but of the speed of light and the age of everything. The universe, as we understand it, began about 13.8 billion years ago. That means the oldest photons, messengers of distant suns, have only had 13.8 billion years to travel. And so, our cosmic horizon is like a glowing sphere carved by light itself, a bubble of what we can see, ringed by what we can only imagine. You're not standing at the center of the universe, but you are standing at the center of your own observable one. Every direction you look, north, south, up, down, forward, backward, is a line into history. Each photon you catch is a memory of the universe as it was long before you ever existed. Light from nearby stars might be a few years old, but light from the oldest galaxies? It's been traveling since before Earth had oceans, before atoms were organized into anything we'd call life. Imagine it. You are surrounded by time itself, by ancient light arriving just now, just for you. But past that, past the most distant, redshifted glow, past the veil of the cosmic microwave background, lies a realm you can never touch, the rest of the universe. And if the laws of physics are consistent, it doesn't end there. This invisible wall, this light speed limit, is known as the particle horizon. It forms a shell 46 billion light-years in every direction. That's bigger than 13.8 billion, you might be thinking. But space itself has been expanding the entire time those photons traveled, like painting dots on a balloon as it inflates. Those distant galaxies have moved ever farther away while their light raced toward us. So the universe we can see is a 93 billion light-year wide bubble and growing. But outside that bubble, no telescope, no satellite, no beam of light can go beyond. Not now, not ever. Not because there's nothing out there, but because even if there's everything out there, we are locked inside the speed of light. We are bounded by time. And here lies the paradox. The universe, as far as we can tell, doesn't have a true edge. No curtain drop, no finish line. There's no moment where galaxies run out, where time ceases, where the grid of reality breaks off into digital static. Instead, space might go on forever, an infinite, unobservable vastness, stretching beyond our comprehension. Or maybe, just maybe, it curves back on itself. A loop, a bubble, a topological illusion, like walking forward forever, only to return where you began. But either way, we'll never know from here, because the truth isn't hidden behind some distant mountain we've yet to climb. It's hidden behind the fabric of space itself, always stretching, always expanding, always placing the horizon further away than we can chase. The cosmos, like a receding dream, slips away faster than we can run. There is something haunting in that. You look up, and you're seeing the past. You build bigger machines, and you're seeing the deeper past. You think you're uncovering the secrets of the universe, but you're just peeling back the layers of your own blindness. We are creatures of boundaries, borders, edges, limits, the edge of the map, the edge of the sea, the end of the world, but the universe laughs at our metaphors. It stretches and swells and whispers what you call the end, is just where your candle stops glowing, and perhaps that's the most beautiful part of it. The horizon is not a punishment. It's an invitation, a cosmic dare. It says, you will never see everything, but you will never stop trying. Let's be clear, what we see is not all that exists. It's just all that light has allowed us to witness. Beyond our cosmic horizon could be trillions more galaxies. Galaxies like ours? Galaxies with stars, with planets, with life, with stories, with mysteries deeper than our physics can imagine. And they will live and die without us ever knowing. Their light will never reach our eyes. Their gravity will never tug on our telescopes. Their radio waves will never whisper across our void. They are lost to us not because they're gone, but because space is faster than light. They are on the other side of the universe. Not in distance, but in reachability. So next time you look at the night sky, remember, you are not looking at a place. You are looking at a time boundary, a limit drawn not in miles, but in moments. Every star you see, every galaxy your telescope captures, it's a ghost of what once was. And beyond them, a silence that screams not emptiness, but unknowability. That's what lies on the other side of the universe. Not a wall, not a destination, but a question mark painted in starlight. And we tiny, temporary beings built of carbon and dreams are still daring to ask what lies beyond it. What if the cosmos has no edge, because it was never meant to end? Infinity, a word we use casually, but when taken seriously, it becomes a mirror that warps everything we believe. What is infinity, really? Is it a place, a direction, a number, or is it a boundaryless state of mind, a concept not meant for creatures born in a womb, bound by gravity and limited by breath? We say the universe might be infinite, stretching forever in every direction, beyond our horizon, past the light of the earliest stars, and even further still. But if it truly is infinite, then what are the implications? Is infinity real, like a continent we've yet to explore? Or is it an illusion born from the limits of our language and imagination? If the universe is infinite, then somewhere out there, farther than even light could ever hope to travel, there must be another Earth. Not just a similar one, but an identical one. Same oceans, same clouds, same cities, same you, reading these words again. And not just one, an infinite number of yous, slightly different, drastically different, some better, some worse, some never born, some born into stars. This is not science fiction. It is what follows if space goes on forever, and matter distributes roughly the same way it does here. Every possible configuration of particles must eventually occur, and recur, endlessly. But let's pull back. Why do scientists think the universe might be infinite? Part of it comes from Einstein's equations, the theory of general relativity. These equations don't demand an edge. In fact, in many solutions, they seem to avoid it. Instead, they describe a universe that is either flat and infinite or curved and unbounded. Think of it this way. If space is truly flat, meaning parallel lines never meet, and the angles of a triangle always add up to 180 degrees, then it behaves like an endless sheet of paper. And that paper, unless torn or curled, never stops. On the other hand, if space is curved, it might loop back on itself like the surface of a sphere. You could travel forever in a straight line and eventually return to your starting point, not because you hit an edge, but because the space you're in is folded in a way your senses can't grasp. In either case, there's no wall, no edge, no outer shell, just continuation. But even continuation can be deceptive. Infinity in mathematics is well defined. It behaves. It fits into equations. You can add to it, subtract from it, and still call it infinite. But in the physical world, things are never so clean. If the universe is infinite, then it has infinite stars, infinite galaxies, infinite versions of you, of me, of everything. But can anything physical truly be infinite? That's where philosophy and physics begin to clash. Infinities in science often signal a breakdown, not a breakthrough. The singularity at the center of a black hole, infinite density. The moment of the Big Bang, infinite energy. But most physicists believe these are warning signs, markers that say, Your current theory stops working here. They're like red lights in the mathematics, places where the equations shout back, "You've asked a question I cannot answer." Still, the possibility of an infinite cosmos persists, and with it come disturbing implications. If the universe is infinite, then our place in it shrinks to nothing. We are not just a speck in a galaxy, in a cluster, in a supercluster. We are one of infinite configurations, a drop in an endless ocean of realities. Our uniqueness, statistical noise. Our meaning, a question lost in the static. Unless meaning is not derived from rarity, but from consciousness itself, from the act of asking, from the courage to wonder. There's another possibility, that infinity is a mirage, a trick of incomplete measurement. Perhaps space only appears infinite because we haven't seen its curve, like being inside a foggy balloon, unable to see its roundness. Perhaps it loops gently, so wide and subtle that even billions of light years can't reveal the twist. In this view, the universe is not infinite, but finite and unbounded, limited in volume, but with no edge. This is what scientists call a closed universe. Like the surface of Earth, it has a total size, but you could walk it forever and never fall off. There's no border, no fence, just continuity. Einstein liked this idea. He once imagined the universe as a four-dimensional hypersphere space, curving back into itself, a self-contained, elegant system. But modern observations, especially of the cosmic microwave background, CMB, suggest the universe is very close to flat. So flat, in fact, that if it does curve, the radius is likely far beyond what we can see. And that brings us back to the same haunting conclusion: we may never know. Because whether the universe is infinite or just incredibly vast, either way, our ability to measure its full shape may be permanently limited. Infinity has another face: time. If space might be infinite in size, can time be infinite in duration? The Big Bang gave us a beginning, but will there ever be an end? If the universe continues to expand, and if dark energy keeps pushing galaxies apart, then time may stretch on forever. A slow, cold, dissolving infinity. No fire, no collapse, no bang. Just entropy, the slow fade into heat death, a state where stars die, black holes evaporate, atoms decay, and nothing new is ever born again. An infinite future without story. That's one vision. Another says the universe will cycle, that after expansion comes collapse, a big crunch, followed by a big bounce, birthing a new cosmos. Endless rebirth. Time is a circle, not a line. But again, the data is silent. And so, infinity remains not an answer, but a landscape of unresolvable questions. Here's the deepest paradox of all. We are finite minds inside a possibly infinite universe, trying to understand what that means. We ask, how big is it? How long will it last? Where does it end? But maybe those are the wrong questions. Maybe infinity is not a thing to be measured. Maybe it is a concept we invented, because we cannot accept an end and cannot grasp a beginning. Maybe infinity is not out there. Maybe it's inside us. A reflection of the part of us that refuses to stop asking even when the sky no longer answers. What if the universe isn't endless, but still has no edge? We are used to edges. Edges define our world. The edge of a cliff, the edge of a map, the border between countries, between land and sea, between sky and space. But when we ask, where does the universe end? Nature shrugs. Not because there's nothing there, but because the question doesn't even make sense. In the language of the cosmos, there may be no edge at all. And yet, space might still be finite. How? Through the strange geometry of curved space where boundaries vanish, but the whole remains measurable. To understand this, we need to think topologically. Imagine you're a two-dimensional being, living on the surface of a balloon. Your world has only length and width, no up, no down, no concept of outside. As you walk, you never find an edge. You just loop around, unaware that your 2D plane is actually curled into a sphere. Now imagine the three-dimensional equivalent. Our universe may be like the surface of that balloon, only instead of curving through space, it curves through higher dimensions we cannot perceive. You can travel straight forever and end up where you started. Not because space is infinite, but because it wraps around itself. This is called a finite but unbounded universe. It doesn't go on forever, but it also doesn't end. This idea isn't science fiction. It's grounded in Einstein's theory of general relativity. Einstein showed that space and time are not rigid. They bend and warp in response to energy and mass. A star curves the space around it, causing light and matter to follow those curves. A galaxy distorts space-time like a bowling ball on a trampoline. Now scale that up. If the entire universe has enough mass energy, then all of space itself could curve into a giant loop. No edges, no walls, just an immense curved cosmos. We call this a closed universe. It's like living inside a four-dimensional hypersphere, finite in volume, but endless in journey. There's a second possibility. The universe could be open like a saddle. It curves outward, like the shape of a trumpet bell. In this case, space would never loop back. It would stretch infinitely in all directions. No walls, no wraparound, just infinite curvature into the void. Then there's the flat universe, the simplest of the three, like an endless sheet of paper. No curvature at all. Parallel lines stay parallel forever. Triangles behave like they do in high school. This flat model is what most modern observations suggest. Data from the cosmic microwave background, CMB, the afterglow of the Big Bang, indicates that the universe is extremely close to flat. So close, in fact, that if it does curve, the radius is so vast we can't detect it with our instruments. But flat doesn't always mean infinite. A flat universe could still be topologically wrapped, like a video game world that loops. You exit stage right and reappear on the left. The space feels infinite, but it's actually finite and periodic. A cosmic Pac-Man maze in 3 dimensions. So which is it? Open? Flat? Closed? Infinite? Bounded? Looped? The answer is, we don't know. We live inside the system we're trying to measure, like ants crawling on a beach ball, unable to see the curvature because it's spread over too vast a distance. But we've tried. Scientists have looked for matching patterns in the CMB echoes of light that could have wrapped around the universe more than once. If space is looped, some of those ancient photons should reach us from multiple directions, forming duplicate sky patches. So far, no clear evidence. But absence of evidence is not evidence of absence. Now let's go deeper. What if this wrapping isn't just a trick of space, but of reality itself? Enter the idea of the multiverse. Some versions of the universe may indeed be closed loops. Others may be open and infinite. If cosmic inflation is true, the rapid ballooning of space right after the Big Bang, then the conditions that created our universe might also create others. Bubble universes, each born from its own fluctuation, each with its own laws, its own curvature, its own story. Our universe would just be one bubble in a frothing sea, a tiny patch of an inflating fabric that never stopped expanding. But this raises a chilling possibility. If the universe loops, could it eventually return to its origin? Could we live in a cyclical cosmos, forever expanding, then collapsing, then being reborn? A Big Bang, a cosmic stretch, a slowing, a collapse, the big crunch, followed by another bang, an eternal heartbeat of existence. Some theories suggest yes. Others say no, that dark energy will keep stretching space forever, tearing galaxies apart until the stars fade and the atoms dissolve. In one version, time loops. In another, time dies. The emotional weight of this is staggering. We want the universe to have a shape, a map, a compass. We want to ask, how far until the end? But what if there is no end, not because we're too small to find it, but because there is nothing to find? The universe may be curved like a loop, or flat like a plane, or warped like a saddle, but it may never give us a clear answer. And in that ambiguity lies its power. The universe plays tricks on the mind. It stretches without stretching, ends without edges, loops without turning. We walk through a cosmos that curves beneath our feet, but the arc is too wide to notice. We live in a shape we cannot draw. We dream of answers beyond our dimension. And maybe, just maybe, space isn't the only thing that's curved. Maybe our thinking is too. Maybe the universe isn't some tidy box with walls and labels. Maybe it's a paradox, a riddle, a maze with no center and no exit. And that might be the most beautiful truth of all. What if the true edge of the universe is the limit of time itself? We like to think that with better tools, we can see anything. Bigger telescopes, sharper lens, here orbits, deeper scans. But no matter how advanced our technology becomes, we are surrounded by an invisible wall, not made of matter, but of time and light. A cosmic prison, a horizon not of geography, but of possibility. This is the observable universe, a finite sphere of visibility, carved not by space, but by the age of light. Beyond it, we don't know. We can't know, because light simply hasn't had the time to get here. Here's the hard truth. Light is fast, but it's not instantaneous. It travels at 299,792 kilometers per second, fast enough to circle the Earth 7 times in a second, but not fast enough to cross billions of light years in a moment. And since the universe has only been around for about 13.8 billion years, that means we can only see as far as light has traveled in that time. That's our particle horizon. The farthest we can look, not because that's where the universe ends, but because we haven't been alive long enough to see beyond it. It's not a wall of stone, it's a wall of history. But wait, if the universe is 13.8 billion years old, shouldn't the farthest thing we can see be 13.8 billion light years away? No, because the universe isn't static. It's expanding. While that ancient light was on its journey toward us, space itself was stretching, pushing its source farther and farther away. By the time the light reached us, the galaxy that emitted it had drifted, not moved through space, but been carried by space to a distance of over 46 billion light years. That's why the observable universe is actually about 93 billion light years across. Not because anything traveled faster than light, but because space grew underneath the light as it moved. Imagine releasing a balloon into a river. The balloon floats downstream, but as it does, the river widens, stretching the distance between the balloon and the shore. That's what happens with light and expanding space. The light travels, yes, but the space between us and the source keeps growing. We live in a reality where the ground beneath our measurement tools is stretching. This leads to a strange and sobering realization. There are galaxies we will never see, not because we lack the tools, but because their light will never reach us, even if we wait forever. Why? Because the universe is expanding faster than the speed of light, not locally, but globally. The fabric of space itself is accelerating outward, and that creates a second, more permanent limit, the cosmic event horizon. While the particle horizon marks what we can see now, the event horizon marks what we can ever see, even in the infinite future. Anything beyond it is permanently out of reach. It's a terrifying thought. Imagine watching a ship drift out to sea. You think, if I wait long enough, it will return. But instead, the sea stretches. The current pulls faster than any boat can row. And slowly, inevitably, the ship disappears, not just from sight, but from existence. That's what the expansion of space is doing to the cosmos. We are losing galaxies right now. Their light still reaches us, but it's ancient light emitted billions of years ago. If those galaxies sent new light now, we would never receive it. They are still there, still glowing, still evolving, but they are already beyond the event horizon, gone forever. It gets worse. This horizon is not fixed. It moves, and it accelerates. With each passing moment, more of the universe slips past it, not with a bang, not with a scream, but with a fading whisper, a redshift, a stretch, a disappearance. One by one, the lights go out, not because the stars die, but because the space between us and them grows too vast, too fast. This is not poetic exaggeration. This is cold cosmology. In the far future, the sky will grow empty. Only the galaxies of our local group, gravitationally bound, will remain visible. Everything else, the majestic arms of Andromeda, the glittering webs of superclusters, the echoing light of quasars will fade from view. The universe will look lonely, smaller, quieter, but that will be a lie. The cosmos isn't shrinking. It's slipping away, and we are inside a cage of light, watching the walls recede. We often say the universe is expanding into something, but it's not. Space is not growing into a larger void. It is the thing growing. There is no outside. The universe doesn't sit in a bigger room. It is the room, all directions, all dimensions, all clocks. So when we say we're surrounded by a horizon, it's not like looking at the edge of a cliff. It's like standing inside a dream that's too large to finish. With every second that passes, more of it slips into inaccessibility. And still, despite this loss, despite the limitations, we watch, we measure, we listen, we build instruments to catch the final photons, the last redshifted signals, the whispers of stars that died before Earth was born. Each photon that arrives from the edge of the observable universe is a miracle, a message from a place we'll never reach, a flicker of memory from a cosmos already gone. We treat those photons like sacred relics. We chart them, we map the sky, we listen to the fading hum of the universe as it retreats into silence, and we marvel. The observable universe is not just a sphere of data. It's a window into a grander whole, a way to touch the infinite from within the finite. It reminds us of something primal and humbling. We will never see it all. No matter how long we wait, no matter how far we reach, the universe will always be more than we can grasp. Not because it is cruel, but because it is endless in ways our minds were never designed to contain. And yet, we try. And in that trying, in that reaching, we become something more than particles. We become the universe, asking about itself. What if parts of the universe have already said goodbye, forever? There is a kind of silence you don't hear. You feel it. Not the silence of empty rooms or forests at night, but the silence of distance, of separation so profound, even light gives up the journey. That is the silence beyond the cosmic event horizon. Not a metaphor, not a theory, a real boundary out there, right now, beyond which no signal will ever reach us, no matter how long we wait. It's not that we can't see it yet, it's that we never will. Let's revisit the basics. The universe is expanding, not like fireworks flying away from a central point, but like dough rising, stretching everything within it. Galaxies aren't speeding through space. Space itself is expanding, carrying galaxies with it. And here's the twist. There's no speed limit for the expansion of space. While nothing can move through space faster than light, space itself can stretch as quickly as it pleases. The result? Distant galaxies are receding from us faster than light. Not because they're breaking the rules, but because the rules are bending. Now imagine a boundary. A distance from Earth where, if something crosses it, its light will never reach us. Not even given infinite time. Not because the light isn't trying, but because space itself is outrunning it. This is the cosmic event horizon, a one-way gate, a limit defined not by where things are, but by what can ever interact with us again. Think of it like the edge of a waterfall. Anything beyond the drop is lost to the current. You can wave, you can scream, but nothing comes back. Right now, this horizon is about 16 billion light-years away. That's closer than the edge of the observable universe, 46 billion light-years, but in a more haunting way. Because many of the galaxies we currently see, those whose ancient light is only now reaching us, are already beyond this event horizon. They exist, but we'll never see new light from them again. What we're watching now is their ghost, their past. If they exploded tomorrow, we'd never know. They've already slipped beyond the cosmic curtain. This raises a startling realization. Every second, more galaxies cross that threshold, not because they're accelerating, but because Space Island, the very structure of reality, is pulling them away, like a tide that never stops rising. And the cause? We call it dark energy, a force, or field, or property of space itself that accelerates the expansion of the universe. We don't know what is island. We don't know where it comes from, but it behaves like gravity turned inside out. A pressure that doesn't pull, it pushes. And that push is making the universe's growth exponential, which means the event horizon is not just a line in space, it's a clock. There will come a time, not today, not tomorrow, but someday when the majority of the universe will lie beyond our reach. Even as we improve our telescopes, even as we stretch the limits of measurement, most of the cosmos will become permanently unknowable. Entire superclusters, hundreds of billions of galaxies will vanish from our future. We will see their past, but never their present, never their end. They will become cosmic fossils, trapped in a bubble of memory, their stories half told. This isn't just poetic sadness, it's a scientific wall. In a universe dominated by dark energy, the cosmic event horizon shrinks in terms of what can ever influence us. Imagine launching a rocket toward a distant galaxy. Even if you could send it at light speed, the space between will stretch faster than the rocket can move. It will never arrive. It will never send back a message. That galaxy has become causally disconnected, not gone, but unreachable, like a ship sailing off the edge of a map, not falling, just drifting into fog that never lifts. Here's the deeper pain. Even information cannot cross the event horizon. No matter, no energy, no data, no whisper of existence. It's not a glass wall. It's a vanishing point in the timeline of the cosmos. Whatever happens beyond it, a supernova, a civilization, a collision of black holes, it is lost to us forever. Even gravity waves, those ripples in space-time that move at light speed, are bound by this limit. The event horizon is nature's final no, and yet, it's also a reminder of something profound. We are witnessing a unique era, an age when the sky is still rich with galaxies, when ancient light still arrives at our doorstep, when the cosmos still tells us stories that began billions of years ago. We live in a time where we can still see, and that will not always be true. There will come an epoch when the night sky darkens, not because the stars are gone, but because the universe has grown too vast to contain their light. A future where we look up and see almost nothing. So what do we do with that knowledge? Do we despair? Or do we lean in eyes wide and listen harder while the universe still speaks? Do we treasure each photon like a letter from a friend who will never write again? Do we build better instruments, knowing the windows are closing? Do we tell stories not just of what we see, but of what we will never see again? Because in this fading glow, this retreating cosmos, there is something more powerful than observation. There is awareness. Awareness that we are witnessing the sky's last chorus. Awareness that we are part of the final audience for parts of the universe whose light has taken longer to arrive than Earth itself has existed. The cosmic event horizon is not just a limit. It is a whisper, a countdown, a fading signal. And though it may feel cruel to be shown the universe and then told we cannot follow, there is also beauty in it, because it means this moment is rare. This view, this sky, this access, it is a privilege not granted to all times. We are witnesses to a universe still in bloom, still shedding its light toward us. And so we must honor that by watching, by wondering, by remembering that even when the lights go out, we once saw them. What if the cosmos we see today is already gone? There's a strange kind of grief that comes not from losing something, but from realizing you never truly had it. That's what it feels like to live in a universe we are already losing. We point our telescopes into the abyss and marvel at what we find: ancient galaxies, bursting stars, delicate webs of matter across unimaginable scales. We believe, somehow, that what we see is what island, but the truth is far more haunting. What we see is what was. The cosmos isn't static. It isn't waiting patiently for us to catch up. It's moving, expanding, accelerating. And while we map its structure, the universe silently recedes, not like a thief in the night, but like a dream, dissolving the moment you try to write it down. This isn't poetic drama. It's scientific fact. The deeper we look into space, the further back in time we see. A galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. But the kicker? That galaxy isn't 10 billion light years away anymore, because space has been stretching the entire time that light traveled. It might now be 30 billion light years distant, or 40, and still accelerating. The light we receive is ancient. The galaxy it came from has moved far beyond our reach. We are receiving the past while the present slips into darkness. This phenomenon is known as cosmic redshift. As space expands, it stretches the very fabric of the light waves traveling through it. The photons we observe from faraway galaxies arrive elongated, redder, slower, colder. It's as if the universe is whispering to us, but its voice is fading. And for many of these galaxies, the light we're seeing today is the last light we'll ever receive from them. Even if they continue shining for trillions of years, even if they give birth to stars, even if they build civilizations, their stories will never reach us again. They are already on the other side of forever. In 1717 Devon, astronomers studying distant supernovae made a stunning discovery. The universe isn't just expanding, it's accelerating. Instead of slowing down after the Big Bang, the cosmos is picking up speed, like a car with no brakes, being pushed by some invisible hand. That hand is what we now call dark energy, a force woven into the fabric of space itself. We don't know what it island, but we know what it does. It drives galaxies apart. It stretches the universe faster and faster. It's pulling the sky out from under us. Every second, more regions of space are moving away from us faster than the speed of light. Not because they're violating physics, but because space itself is growing that fast. And once something crosses the event horizon, that invisible boundary we discussed, it's lost permanently. The tragic beauty of this moment in cosmic time is that we live in the last generation that will see the universe as it truly island. In a few trillion years, if conscious beings still exist, they will look up and see nothing. No distant galaxies, no expanding web of cosmic filaments, no Big Bang to remember. They'll live in a cosmic bubble, floating in apparent isolation, with no evidence of anything beyond their local group of galaxies. To them, the universe will look small, static, cold. The truth of the cosmos, the magnificent dance of galaxies, the echo of inflation, the traces of the Big Bang will be hidden, gone, erased by time and distance, and they'll never know. But we do. We live in a golden era, a fleeting window, where light from across the universe still reaches us. We see the infant galaxies. We trace the ancient redshifts. We hear the fading hum of the cosmic microwave background, the echo of creation itself. Every image we capture, every faint glimmer, every ghostly silhouette of a faraway galaxy is a time capsule, a sacred fragment of a universe that has already moved on. It's like watching old footage of a loved one and knowing they're no longer here. So what do? We measure, we map, we remember. We build instruments not just to see, but to preserve, because the light arriving now is not just data. It's the last whisper of regions we'll never hear from again. Every photon is a farewell. Every spectrum is a goodbye. But embedded in that goodbye is a message. I was here, and that matters. Some people ask, why does it matter if we can't reach those galaxies? If they're gone from us, why mourn them? But this misses the point. It's not just about reach. It's about wonder, perspective, connection. We are not isolated accidents. We are part of the grand unfolding. The fact that we can see what we do even for a moment is a miracle of physics, timing, and existence. We were born into a universe that still remembers itself, and in remembering it, we become part of the memory. So here's the truth. The universe is slipping away, not because we failed, not because we were too slow, but because this is the nature of reality. Expansion, separation, change. We are not the authors of this story, but we are its readers. And this page right now may be the most profound one ever written. A page where we still see the echoes, still catch the light, still dare to ask, what lies beyond this moment? Because in the vast silence to come, that question and our asking of it might be the last thing the universe ever hears. Every photon, is a memory stretched thin by time. Imagine standing on a shoreline, watching a message in a bottle drift in from the sea. The ink is faded, the paper brittle, the language foreign, ancient, trembling with time. And yet, you read it. Now imagine that bottle traveled 13 billion years, not across an ocean, but across the expanding fabric of the universe. That's what every photon from a distant galaxy island, not just light but history, not just information, but evidence that something once was. And the further it travels, the more distorted it becomes. Its color bleeds red, its voice slows to a whisper, its energy becomes a fading echo. This is cosmic redshift, and it's not just an astronomical curiosity. It's the most beautiful funeral procession in physics. Let's understand the phenomenon first. When an ambulance drives past you, its siren changes pitch high as it approaches, low as it moves away. That's the Doppler effect. Light behaves the same way. When something moves away from us in space, the light it emits stretches. The wave crests get further apart, the energy dilutes, and the wavelength shifts toward red, the low-energy end of the spectrum. But here's the catch. These galaxies aren't moving through space like cars on a highway. Space itself is stretching. So when light travels from a distant galaxy toward us, it's not just moving, it's being pulled apart. That stretching of the light wave, caused not by motion but by expanding space, is called cosmological redshift. It means the light we see isn't just old, it's tired, worn thin by the journey, bent by the bones of the universe, and yet it made it. Redshift isn't just a measure of distance, it's a time machine. The higher the redshift, the older the light. The further back we're peering into the history of the cosmos. A redshift of 1, we're seeing the universe as it was when it was about 6 billion years old. A redshift of 5, we're now watching light born when the universe was just a toddler 1.2 billion years young. A redshift of 10, 12, 13, we're reaching the cosmic dawn, the first galaxies, the first stars, the first lights to pierce the darkness. The redder the light, the closer we get to creation, to the edge of time, to the Big Bang itself. But that edge isn't sharp. It's smeared, blurry, faint, because the light we crave, the earliest, most ancient signals, is so redshifted, it's nearly invisible. Infrared, microwave, radio. To see it, we need instruments built not for brightness, but for patience and hope. This is where telescopes like James Webb step in. Unlike Hubble, which sees in the visible spectrum, Webb was designed to see infrared, the stretched out remnants of ancient light. It doesn't look at galaxies as they are, it listens to galaxies as they were when they were still forming, still colliding, still screaming into existence. James Webb sees the ghosts of fire, still warm from the Big Bang's first breath. Redshift is not just a clue to distance, it's a scar of expansion, a silent testimony to how fast the universe is moving apart. And it's a reminder that the further we look, the more we're chasing phantoms. Here's the mind-bending part. Some light has been so redshifted, it no longer exists in the realm of light at all. It's stretched into radio waves, into whispers below the range of our vision, into signals that, to us, resemble silence. But that silence isn't empty. It's saturated with memory. Redshift tells us that even the emptiest parts of the sky are drenched in the echoes of galaxies long gone. It tells us that what we perceive as blackness is actually saturated with the past. We just don't have eyes old enough to see it. There's a quiet tragedy in redshift, because the more we understand it, the more we realize the night sky is not what it seems. It's not a fixed dome of eternal stars. It's a slideshow of a universe that has already changed, already moved on. Every glowing dot we see may be dead, gone, or unreachable forever. And the galaxies whose light is just now arriving, they are already lost to us, their current selves receding faster than the speed of light, carried away by dark energy's relentless push. We are surrounded not by what is, but by what was redshifted memories, bleeding through time. And yet, that knowledge is not despairing, it's transcendent, because it means that the universe is not silent. It's speaking, just in a tongue stretched by age, a language carved into Redshift, a poem written in photons that took billions of years to arrive and only seconds to be absorbed by your eyes. We are the final page on which the universe's opening chapters are written. We are light's last reader, so next time you look up and see that faint glimmer, remember, you're not just looking at a star, you're reading a story that began before Earth, before the Sunday, before time as we know it. And even though that light is old, even though it's stretched and tired, it reached you, and that alone is a miracle. One redshifted photon at a time. The telescope that doesn't just look far, it looks before. In the beginning, there was darkness, not because there was nothing, but because the first light hadn't had time to arrive. In that primordial gloom, hydrogen gas cooled, stars began to form, and galaxies started to cluster, like embers flickering into being. But for us, here and now, that ancient light has traveled so far, for so long, that it's been stretched, redshifted beyond the visible, into the infrared. And so, to see it, we built a machine that doesn't just see light, it listens to whispers from the womb of time. That machine is the James Webb Space Telescope. Not a telescope, a time traveler made of gold and mathematics. Webb doesn't see stars the way we do. It doesn't care about twinkling lights or visible brilliance. It hunts for heat, the gentle warmth of ancient suns whose light has cooled with age. Like an interstellar archaeologist, it digs beneath the visible spectrum, peeling away the glowing skin of the cosmos to reach its cosmic bones. It doesn't point toward the future. It plunges backward, toward the fire. In July 2022, James Webb released its first images. And they weren't just pictures, they were proclamations. A deep field, a pinprick-sized view of the sky, revealed thousands of galaxies, each filled with billions of stars. Some of that light had traveled over 13 billion years to get here. That's not just early universe. That's cosmic infancy, the first 300 million years after the Big Bang. And Webb saw it clearly. For the first time, we glimpsed galaxies not as ancient relics, but as newborns. Clumpy, chaotic, full of gas and fire, still being shaped by the gravitational music of dark matter and chaos. We weren't just looking far, we were witnessing creation. But Webb wasn't built just to take pretty pictures. It was built to answer one of the oldest questions in existence. Where did we come from? To answer that, we have to understand how stars were born, how galaxies evolved, how elements like carbon and oxygen were forged in the cores of supernovae. All of that, the story of everything, is written in the infrared glow of the early cosmos. And that's Webb's language. Its golden mirror, 6.5 meters wide, collects that ancient light like an ear tuned to frequencies of the past. Its sensors, colder than outer space itself, detect the faintest warmth of a distant universe. And from that warmth, it reconstructs history. But Webb is more than a camera. It's a thermometer for galaxies, a spectroscope for atmospheres, a detective searching for the fingerprints of life. Because even now, as it peers into ancient galaxies, it also glances at exoplanets, worlds orbiting distant stars, worlds whose atmospheres might contain water, methane, or oxygen. That means Webb isn't just showing us what was. It's asking, who else might be watching their own skies? It's bridging time with possibility, folding the cosmos inward until ancient stardust and modern curiosity touch. But there's a bittersweet truth hidden inside Webb's success. Even with this miraculous machine, we can never see it all. There is a horizon we cannot pass, a cosmic edge beyond which no light, no matter how redshifted, will ever reach us. Those galaxies are already gone from our observable universe, swept beyond by the accelerating expansion of space. Webb can see further than any human eye, but even it is limited. We built a machine to see the beginning, but not the infinite. There is light that has already passed us, and light that will never arrive. And that's the tension of being alive in this moment. We are perched at the perfect cosmic window, far enough from the beginning to see it, but still close enough that the past is not yet lost. So when you look at Webb's images, remember, you are not looking at galaxies. You are looking at time held still. You are looking at the universe becoming aware of itself. Because each image is a mirror, not of our world, but of the possibility that we are not alone and never were. Webb is not just a tool, it is our interstellar memory, a golden eye staring backward through time, so that we might finally understand our place in the vast, expanding poem of existence. And in the darkness beyond Webb's gaze, there are still whispers, still songs, still stories waiting to be seen, because even the best telescope cannot hear all the light. But it reminds us that light once was, and maybe, just maybe, it will be again somewhere, someone else, looking back at us. The faint whisper of the universe's first breath. Before galaxies, before stars, before atoms, there was heat. And when the universe was just 380,000 years old, an infant wrapped in fire, that heat did something miraculous. It let go. Light, once trapped in the soup of particles and plasma, was finally free to travel. It scattered in every direction, no longer bumping into matter, but coasting endlessly. That moment, a turning point in the history of everything, left behind an afterglow. Not a flash, not a flame, a whisper. That whisper is still here. It's called the cosmic microwave background, the oldest light in the universe. But don't be fooled. It isn't light like you know it. It's not yellow, blue, or white. It's not bright or burning. It's cold. It's faded. It's stretched into microwave radiation after 13.8 billion years of cosmic expansion. But it is still there, like a scar from the moment the universe was born. Imagine this. You're standing in the deepest cave, eyes shut. No sound, no wind, no breath. But then, a pulse, a vibration so faint, you question whether it's real. That's what scientists discovered in 1965. Two radio engineers, Arno Penzias and Robert Wilson, were trying to get rid of noise from their antenna. No matter what they did, cleaning, retuning, aiming, the hum remained. It came from every direction. It wasn't interference. It was the sky itself speaking. They had found the relic light from the Big Bang, proof not just that the universe began in fire, but that the fire left a fingerprint, a perfectly uniform background radiation, with slight variations, no stronger than 1 part in 100,000. Those tiny variations? They would become everything. Galaxies, stars, planets, us. Look at the map of the CMB, a false-color globe of blues and reds. What you're seeing are the seeds of structure, slight fluctuations in temperature and density caused by quantum ripples stretched across space during inflation. Where it was slightly denser, gravity pulled harder, matter gathered, galaxies formed. It's the cosmic DNA of the universe, a baby photo not of our galaxy, but of reality itself. But here's the beautiful paradox. The CMB is both the oldest light in the universe and the farthest thing we can ever observe. Why? Because it's the limit of what photons can tell us. Before the CMB, light couldn't travel. The universe was opaque, a fog of charged particles. So anything that happened before that moment, it's invisible to telescopes. There is no older light. The CMB is the cosmic curtain. Beyond it, only silence. Unless we find a new way to see. Physicists dream of detecting gravitational waves from before the CMB, primordial ripples in space-time created during the universe's first trillionth of a second. If we could hear them, it would be like listening to the universe's actual birth cry, not the echo, the scream. Experiments like LISA and ground-based observatories may one day catch those echoes. But for now, the CMB is the first page of the universe's readable story. Everything before it remains locked behind the wall of light. And here's the quiet heartbreak. That wall isn't just far, it's forever, because the universe is expanding. That ancient light is drifting further away. And as it does, it stretches, cools, fades. Billions of years from now, the CMB will be so redshifted, so diluted, it may disappear from detectability altogether. Future civilizations may never see it. They might live in a universe too empty, too silent, to remember how it began. They'll look up and see only darkness. and they'll wonder, was there ever a beginning? We, today, stand at a rare moment when the light of creation is still visible, still measurable, still whispering truth. We are, in a very real way, the cosmic middle children, old enough to know where we came from, young enough to still hear the voice. So the next time you microwave a burrito, remember, you're surrounded by a much older microwave, one that's been humming since time itself turned transparent. Every second, that radiation passes through you, through Earth, through everything. It doesn't stop. It doesn't ask permission. It's just there, the cold, silent glow of before. Not burning, not blinding, but eternal. And beyond that glow, we now enter a realm without light, without photons, without certainty, because what lies before the light is the greatest mystery of all. Listening to the ripples of creation beyond the wall of light, the universe once screamed, not with sound, not with light, but with the violent shudder of space-time itself. Before atoms formed, before light escaped, before the cosmic microwave background flickered into being, the cosmos trembled, and those tremors, they still ripple through the fabric of everything. They are gravitational waves, not particles of light, but distortions in the very scaffolding of space and time. Like ripples across a vast cosmic ocean, they carry whispers from the deepest epochs, from moments we can never see, because where light cannot reach us, gravity might. In 2015, we finally heard it. Two black holes collided over 1 billion years ago. They spiraled toward each other in silence, then in a fraction of a second merged, and that union sent ripples out through space-time. Those ripples traveled across the universe, through stars, through galaxies, through Earth. We built detectors LIGO and Virgo to catch the tiniest stretch and squeeze in the arms of laser-beamed machinery. And then it happened. A blip, a chirp, a vibration in space-time itself. We didn't see it. We felt it. The first direct evidence that Einstein was right. Gravitational waves exist. Space itself can move. Now, scientists believe there may be gravitational waves not just from black holes but from the Big Bang itself. Ripples from the birth of time. Waves that raced outward as the universe expanded, carrying the fingerprint of inflation, that brief, blinding moment when space grew faster than light. These primordial gravitational waves would be unlike anything we've detected. Older than photons, older than atoms, older than light. If we can hear them, we can finally peek behind the curtain of the cosmic microwave background, behind the wall of light, into the dark silence of creation. But detecting them is hard. They are faint, buried in the static of the cosmos. They stretch and squeeze space not by meters or millimeters, but by fractions of a proton's width. It's like listening for a whisper in the middle of a hurricane, or trying to feel the ripple of a pebble tossed into a galactic ocean. Still, we try. LIGO is being upgraded. New observatories are rising. LISA, a gravitational wave telescope that will float in space, arms millions of kilometers wide. There's BICEP, scanning the CMB for circular patterns, a potential imprint of those early ripples. We are building ears for the dark, because light has limits, but gravity does not care. Gravitational waves are not blocked by matter. They are not scattered, absorbed, or slowed. They glide through the hearts of stars, through the void, through you. Right now, your body, your bones, your cells are being nudged ever so gently by ancient waves from distant collisions. You don't notice. You weren't meant to, but the universe is speaking through them, and one day, we might decode its first words. The implications are staggering. If we can hear gravitational waves from the Big Bang, it will rewrite cosmology. We'll know how inflation began. We'll glimpse the earliest fractions of a second, the raw chaos before order. And maybe, just maybe, we'll hear signs of other universes. Because some theories suggest that in those first trillionths of a second, our universe bubbled into existence among countless others. And when those bubbles collided, they might have sent out ripples, not in light, but in gravity. The bruise of another universe could be carved into the waves we're only now beginning to hear. So we listen, to the nothing, to the silence, not for sound, but for motion. Because in a universe born not from a word, but from a wave, the truth may not shine, it may shiver, and in that trembling there is hope, hope that we're not alone in this cosmic sea, hope that beyond the limits of light there are answers, maybe even others. We have stared at the sky for millennia. Now we listen to the very structure beneath it. Like seismologists studying an earthquake to understand Earth's core, we study the echoes of ancient collapses to understand the beginning of everything. Because before there was light, before there was matter, there were only waves. The moment the cosmos became bigger than imagination itself, what if everything we see today, galaxies, stars, time, even space, exploded into being not slowly, but in a flash so fast it defies reason? Not the Big Bang, as you've imagined it, but something even more shocking. A moment when space itself ballooned, not from a spark, but from an unstoppable runaway expansion, faster than the speed of light, faster than causality, faster than thought. This is not science fiction. This is cosmic inflation, and it may be the most mind-bending chapter in the story of everything. Let's rewind the clock, back to a fraction of a second after the universe was born. Not seconds, not milliseconds. Try a trillionth of a trillionth of a trillionth of a second. At that instant, the universe was smaller than a proton, hotter than a billion suns, more violent than anything we've ever known, and then it exploded, not with fire, but with expansion. In less time than it takes for light to cross an atom, the universe expanded by a factor so large it's barely describable, from subatomic size to something billions of light years across. That's cosmic inflation, the event that took the universe from nothing to everything. This wasn't the Big Bang as an explosion into space. It was space itself inflating rapidly and exponentially. Think of a balloon being blown up. At first, the rubber stretches slowly. Then, in one furious breath, it swells beyond recognition. Except now imagine that balloon is the very structure of space-time. And that breath, it wasn't air. It was the vacuum energy of the universe itself, unstable, chaotic, desperate to release its potential. This energy drove space to expand with such ferocity that even light couldn't keep up. In those moments, the universe outran itself. But why did this happen? We don't fully know, and that's the mystery that haunts cosmologists. What we do know is that inflation solves cosmic riddles that otherwise break the universe. Like why the cosmos looks flat, a huge coincidence without inflation, or why the temperature of the universe is so uniform in all directions, even though there hasn't been enough time for light to travel between those distant regions and even things out. Inflation explains both. By stretching space faster than light, it smeared out the wrinkles, made distant regions start close together before flinging them apart. It's like taking a wrinkled bedsheet and snapping it in one violent motion. Suddenly, it looks smooth, even almost perfect. That's what inflation did to space. It smoothed the chaos, but this expansion didn't last. Like a spring unwinding, inflation eventually slowed, dumping its energy into the cosmos in a furious wave of heat and particles. This is what we traditionally call the Big Bang. The fireball wasn't the beginning. It was the aftermath of inflation ending. Inflation set the stage. The Big Bang walked onto it, and from that moment forward, time ticked. Matter clumped, light escaped. The universe, as we know it, began. What's wild is that inflation didn't just create space. It created possibility. Quantum fluctuations, tiny jitters in the early vacuum, got stretched during inflation. Those tiny jitters became the seeds of galaxies. The reason why matter isn't evenly spread, why some places collapsed into stars and black holes. The most delicate ripple in the quantum fog became the reason we exist. We are the children of quantum noise amplified by cosmic inflation. Out of silence came pattern. Out of chaos came structure. Out of nothing came you. But here's where it gets even more surreal. Some versions of inflation say, it never really ended. It ended here, in our bubble, in our observable universe. But elsewhere, inflation may still be happening, endlessly, creating new bubbles, new universes, new realities. This is the idea of eternal inflation, where the Big Bang wasn't a one-time event, but one of countless births in a frothing multiversal sea. Each bubble universe, like ours, expanding within its own laws, its own constants, its own physics. Some may collapse, some may never form matter, but some might be like us, and they are unreachable, because inflation drove them apart faster than light, forever sealing them behind walls we can never cross. So the next time you look up at the stars and feel small, remember this: you live in a bubble born from a quantum breath, a breath that turned nothing into everything, a breath that may still echo elsewhere. Cosmic inflation didn't just shape our universe, it whispered the possibility of others. What if the Big Bang never stopped? Imagine a storm, not on Earth, not on any planet, but in the very fabric of existence, a cosmic storm that births entire universes and never ends. This is not poetry, it's not science fiction, it's the logical conclusion of one of the most powerful ideas in modern cosmology: eternal inflation. We often speak of the Big Bang as a single moment, one blast, one beginning, one universe. But what if our universe is just one bubble in a vast foaming sea of infinite others? A multiverse, not made of parallel timelines, but of bubble realities, each birthed by a cosmic inflation that never stopped. This is the sea we may float in, a multiverse of possibilities, a mosaic of creation. Let's go back. Inflation, this sudden burst of expansion, wasn't a clean, uniform event. It was quantum, unpredictable, like a match flickering in the wind. While inflation ended in our region of space, triggering our Big Bang, it didn't end everywhere. In fact, according to quantum theory, the very nature of inflation means some regions keep inflating, even as others stop. And those regions? They give birth to new bubbles, new universes. This process doesn't just repeat, it accelerates. It's exponential, just like the inflation itself. A single bubble forms, then two, then four, then a trillion. This is eternal inflation, and it means that the multiverse isn't just possible, it's inevitable. Now imagine this. Each bubble is like a closed universe, with its own space, time, and physical laws. Gravity might be weaker, atoms might not form, light might move differently, time might bend in ways we can't imagine. Most of these universes would be hostile to life, dead before they begin. But others might thrive, with stars, with chemistry, with consciousness, maybe even with their own versions of us, or something far stranger. And here's the kicker: these universes are forever separated. The space between bubbles expands faster than light, driven by inflation still raging outside them. There is no path to reach them, no probe we can launch, no signal we can send. They exist if they exist beyond our eternal reach. They are part of the cosmos, but forever hidden from our sky. Does this sound unprovable? Maybe. But eternal inflation isn't just speculation. It's a mathematical consequence of what we already believe. The same equations that explain the smoothness of our universe, the structure of the cosmic microwave background, and the seeds of galaxies also suggest this endless spawning of bubble universes. And some physicists argue it's more likely that a theory produces many universes than just one. In fact, the idea that only one universe formed might be the weirdest assumption of all. This changes everything. It means the question, why is the universe just right for life, isn't our mystery, its inevitability. In a multiverse, everything happens. Every possible configuration of physics plays out somewhere, and we happen to live in the universe where the dice roll just right, where stars live long enough, where atoms bind, where consciousness can bloom, not because it was designed, but because in an ocean of universes, some were bound to support life, and only those can ask the question. But let's not stop at theory. What if the observable clues of other universes exist? What if subtle anomalies in the cosmic microwave background, those faint temperature ripples, are the scars of bubble collisions? Moments when another universe brushed ours like ships in the night? These ideas are speculative, but not impossible. Future missions might scan the sky, not just for stars, but for the bruises of the multiverse, and even if we never detect them, even if the multiverse stays silent forever, the idea lingers that we are part of something vaster, that our Big Bang is just one verse in a much grander cosmic song, a single note in an infinite chord. In this vision, our universe is not the universe. It is one breath among infinite exhalations, one flame in a field of fire, one reality among endless dreams. How do we measure the unfathomable? Out here, in the silence of the stars, distance loses meaning. There are no road signs in the cosmos, no mile markers, no sound bouncing off canyon walls. Just light, just time, just whispers stretched across the void. And yet, from our tiny perch on a pale blue dot, we have dared to measure the impossible, to chart the depths of an expanding universe, to climb the very ladder of cosmic distance, rung by rung, from our moon to the edge of the observable universe. This is how we measure the unmeasurable. Let's start with the first rung, parallax. A method so humble, yet so profound. It begins with Earth itself. As our planet orbits the sun, we observe nearby stars from different angles, January versus July. The stars shift ever so slightly in the sky. That shift, called parallax, is tiny, minuscule, measured in arc seconds. But from this wobble, we triangulate. It works for the closest stars just a few hundred light years away. But beyond that, the angles vanish. Space laughs in silence. So we reach higher. Next rung, Cepheid variables. These are stars that pulse bright, dim, bright again like cosmic lighthouses. And here's the magic. Their pulsation period directly correlates with their intrinsic brightness. Measure how long a Cepheid takes to brighten and fade, and you know exactly how bright it truly island. Compare that to how dim it appears from Earth, and you've got its distance. This discovery, thanks to Henrietta Leavitt, revolutionized astronomy. Suddenly, galaxies were no longer fuzzy clouds. They were island universes millions of light years away. But what about even farther? Galaxies across cosmic gulfs? That's where Type Ia supernovae explode into the story. These are dying stars that ignite with uniform fury. They shine with near-identical brightness, becoming, for a few weeks, brighter than entire galaxies. We use them as standard candles. If one erupts in a galaxy, we measure its apparent brightness and compare it to the known luminosity of that supernova type. Like a lighthouse on a distant cliff, it tells us, I am this bright. If I seem dim, you are far. And from that, we leap across billions of light years. But light alone is not enough. We must account for its journey through expanding space. Enter Redshift. As galaxies speed away, their light stretches, sliding toward the red end of the spectrum. The more redshifted it is, the faster it's moving away. And, thanks to Hubble's law, the faster it's moving, the farther it must be. So we match redshift to distance. A kind of Doppler radar for the cosmos. It's not perfect. Gravity distorts, space bends, dark energy twists the rules, but it gives us a map, a cosmic GPS, guided by photons stretched like ancient violins. And there's more. Surface brightness fluctuations, Tully-Fisher relation, gravitational lensing, each a Cleverung, each a way to extend the ladder deeper into the unknown. We calibrate them all, from the moon to the nearest stars, to nearby galaxies, to supernovae in galaxies far beyond. Each rung builds on the one below. One misstep, and the whole ladder crumbles. This is science as scaffolding, built on precision, on trust in the light. But there's a twist. As we've refined our ladder, something strange emerged. A tension, two ways of measuring the universe's expansion rate. Hubble's constant give different answers. One, using the early universe via cosmic microwave background. The other, using the distance ladder via local galaxies and supernovae. And they don't agree. It's not just noise. It's a crack in the cosmic mirror, Some physicists whisper of new physics, of dark energy behaving differently, of a universe more complex than we dared imagine. And yet, we continue. We launch telescopes into space. We perfect detectors. We scour the skies for new supernovae. We are building a map of the invisible, a cartography of silence, a ladder that climbs not just distance, but time, because the farther we look, the older the light. When we see a galaxy 10 billion light years away, we see it as it was 10 billion years ago. We are not just measuring space. We are witnessing time travel. Why does this matter? Because only by measuring, only by knowing, can we ask the deeper questions. Where did we come from? How old is the universe? Is it infinite, curved, destined to collapse? Are we alone? The cosmic distance ladder is not just a tool. It's a symphony of methods, a human endeavor to grasp the infinite with finite minds, from parallax to photons, from Cepheids to galaxies. We climb and climb and climb. Ahwong whispers, "You are here, and beyond, there lies more." What is the geometry of everything? Look up at the night sky. It seems infinite, black velvet studded with stars. But behind that beauty lurks a question far more profound than it first appears. What is the shape of the universe? Not the shape of planets, not the shape of galaxies, but the shape of space itself. Is it curved like a sphere, flat like a sheet of glass, or twisted into something stranger, an infinite saddle stretching outward forever? This isn't just a question of geometry, it's a question of destiny, because the shape of the universe determines how it will end. Let's begin with Einstein. His theory of general relativity tells us that mass bends space, and not just objects within space, but space itself. Think of a trampoline. Drop a bowling ball on it. The fabric curves. That's mass warping space-time. So if mass can warp small regions of space, what about all the mass in the universe? Can the entire cosmos be curved? Yes, and it leads us to three possibilities. 1. The closed universe, a cosmic sphere. Imagine sailing across the ocean. No edges, no walls. Sail far enough in a straight line, and you end up where you started. That's a closed universe, like the surface of a 3D sphere, except extended into higher dimensions. In this model, space curves inward. Parallel lines eventually meet, and if you could travel far enough through space, you'd return to your starting point, not because you turned, but because space itself looped around. A universe like this has positive curvature. It is finite, yet unbounded. And its fate? Eventually, gravity wins. The expansion slows, then halts, then reverses, and the universe collapses inward in a catastrophic big crunch. 2. The open universe, a cosmic saddle. Now picture a Pringles chip, or a horse saddle. That's the geometry of an open universe with negative curvature. Space bends outward, parallel lines diverge. Triangles add up to less than 180 degrees. In this model, the universe is infinite. It will expand forever. Galaxies will drift endlessly apart. Stars will die, one by one. Eventually, entropy rules. Everything goes cold, a heat death, a big freeze, an endless, lifeless darkness. 3. The flat universe, infinite and balanced. Finally, we arrive at the middle path, flat space. No curvature, just like the geometry you learned in school. Triangles with 180 degrees, parallel lines that stay parallel. In a flat universe, expansion continues forever, but not wildly, not catastrophically. Instead, it slows asymptotically, forever approaching zero, but never quite stopping. The cosmos becomes a vast, still stage, like a candle that never quite goes out, but never burns brightly again. So which is it? Closed, open, flat? The answer comes once again from the light of the ancient past, from the cosmic microwave background, the afterglow of the Big Bang. The patterns in that light, when mapped with exquisite precision by satellites like WMAP and Planck, tell us something astonishing. Our universe is flat, not curved inward like a sphere, not curved outward like a saddle, but balanced, on the knife's edge between collapse and endless expansion, a geometry so precise it defies belief. To 0.4% margin of error, past space is flat. But here's the twist. Flatness doesn't mean boring, or finite, or even simple, because flat space can still be infinite in extent, or wrapped in strange ways like a torus, a donut-shaped topology where traveling in one direction still loops you back. Even a flat universe can be finite, depending on its topology. And more hauntingly, a flat universe with accelerating expansion thanks to dark energy will still end in silence. Not a collapse, but a fading. So what does the shape of space tell us? It tells us the origin of cosmic structure. It tells us the destiny of all things. And it tells us something spiritual too, that even in vastness, balance is possible. The universe was born on a razor's edge. Too much mass, and it would have curled inward and collapsed. Too little, and it would have shredded itself into empty oblivion. But instead, it found equilibrium, a perfect flat balance. Why? We don't know. Inflation theory helps explain it. Quantum fluctuations seeded it. But the deeper answer may lie beyond physics, in the realm of philosophy, or design, or randomness birthed by eternity. We may never know, but here's what we do know. We live in a universe that is finely tuned, a space that sings in perfect pitch, flat, infinite, and expanding like breath. And in that flatness, we float. What lies beyond the edge of visibility? There is a boundary, a wall, not of matter, not of stone, but of time and light. It's called the cosmic light horizon. It marks the outermost shell of what we can see, the edge of the observable universe, roughly 46 billion light-years in all directions, a sphere of vision, inflated by the speed of light and the age of time. But beyond it, not darkness, not nothingness, just elsewhere, a realm where galaxies continue to exist, stars are born, and cosmic winds still blow, but their light hasn't had time to reach us. And because of cosmic expansion, it never will. We live in a bubble of vision, a glowing prison made of time and velocity. And beyond that bubble lies the unobservable. Let's be clear, the observable universe is not the whole universe. Not even close. It is simply the region from which light has had enough time to reach us since the beginning, and that bubble grows every day. But the universe itself? It's expanding faster than light, which leads to a paradox. Every second, more of the universe slips away, crossing the threshold of reachability. Galaxies that once sent us light will someday send us none, not because they died, but because they outran the fabric of causality. They didn't fall into black holes, they became unreachable. Like ships drifting past the horizon of a black hole, they recede forever. So what lies beyond? Only theories, speculations, poetry written in equations. But let us entertain them, for they are dazzling. 1. More of the same. The simplest answer? More galaxies, more stars, more space. The universe may be infinite, stretching endlessly in all directions, a flat, ever-expanding ocean of matter and energy. Beyond our horizon, there may be clusters of galaxies just like ours, entire regions of cosmic web, mirroring ours in shape, but not in detail, a different arrangement of stars, a different cosmic history, but still governed by the same physical laws. It's familiar, comforting, and yet not the only possibility. 2. The multiverse. Now the ground begins to shake. What if our universe is just one bubble in a frothing cosmic foam? Inflationary theory suggests it. As space expands, quantum fluctuations can cause pocket universes to form, each with their own physics, their own constants, their own timelines. Some might be barren, some might burn too quickly, some might collapse instantly, but some might look eerily like ours. In an infinite multiverse, everything that can happen will happen, somewhere, A universe where Earth never formed, another where dinosaurs never died, and somewhere, statistically, an identical copy of you is reading these same words, only they blinked at a different moment and made a different choice. 3. The meta-cosmic terrain, and beyond even the multiverse, ideas that strain the edges of language itself, mathematical universes, where everything that is mathematically consistent must exist, simulation hypothesis, where reality beyond the horizon isn't far away, it's just not rendered until we look. Higher dimensional spaces, where our 3D universe is a membrane floating in a higher dimensional bulk, each theory more mind-bending than the last, and each one unprovable for now. But here's the deepest mystery. If we can't see beyond the horizon, should we still believe in it? Science says yes, because the laws that govern what we can observe give rise to predictions about what we can't. We extrapolate. We assume continuity. We believe the universe doesn't suddenly end just because we can't see further, but we also remain humble, because maybe, just maybe, there's a great curtain at the edge, and beyond it, something we're not ready to imagine. So where does that leave us? Here, floating in the middle of an expanding infinity, bound by the speed of light, bound by time, bound by perception. But our minds are not bound. We look up, we wonder, we build telescopes that peer into the ancient past, trying to glimpse the shape of forever. We write equations, we tell stories, we search for meaning in the silence beyond the stars. And perhaps, just perhaps, that's what makes us cosmic. Not our size, not our power, but our capacity to ask, what lies beyond? And why is there something rather than nothing? This is the edge of knowing, the final light of what we can see. But it's not the end. It is the beginning of curiosity. The infinite begins where our sight ends. The stars whisper, keep going.